So this video will be about another approach to polynomial approximation, and it's based on a different notion of what it means for a polynomial approximation to be close to the original function. So remember, previously we've been using this notion, this method of measuring how accurate a polynomial is to the original function. We look at the maximum error in the polynomial anywhere in the domain, right? So for any x, we look at the maximum error of p of x. And that's what we've been using up till now. So in this lecture, we're going to focus on a slightly different notion. The idea is, instead of looking at the maximum error, it's more like the average error or the total error. So what you do here is you say, let's add up all the error at all the points x, right? So of course the way you do that is you integrate the error with respect to x over the whole domain. Now actually we integrate the square of the error. There's two reasons for working with the square of the error. One is that it guarantees that this term will be positive, so you won't get cancellations. You wouldn't want to get cancellations in your error, right? If the error is positive in one place and negative in the other, you don't want those to cancel out. You want those errors to still be cumulative. A more profound reason for using the square of the error is that when you use squares to measure the distance between things, like in this case the distance between the approximation p and the original function f, then you can use the Pythagorean theorem, right? Believe it or not, yes, we will be able to use the Pythagorean theorem and use geometric reasoning. Because when you talk about the square of the error, then Pythagoras says a squared plus b squared equals c squared, and you can break things down by right angles, and you can figure out the lengths of the sides and things like that. So by using the square of the error, we will make it possible to use all kinds of geometric reasoning perfectly rigorously. And then at the end, after taking the integral of the square error, we then take the square root to kind of compensate for having taken the integral of the square, right? So, incidentally, these two measures of the size of the error have shorthand notations. This is kind of like L2 error, and this is L infinity error. L is for Lebesgue. He was a very famous mathematician who worked on integrals, and the 2 is for the power here, right? So L2 is because we're doing an integral with of the square. L infinity is a little harder to explain, but it turns out that this notion of error, the maximum error, it's a little bit like replacing the power here with infinity and then taking the infinite root, if you can imagine such a thing. So you actually have to take a limit. So it's a little harder to explain, but there is a sense in which this notion of error, taking the maximum error that occurs anywhere, is a little bit like replacing the power 2 here by infinity. So, as I said, we're now going to focus on this notion of error, and we want to think about how do we find the best polynomial approximation in this sense, right? In the sense of minimizing error according to this definition. So what we want is the projection of the function f to the subspace of polynomial functions. And I mean projection in the same sense in which it was used in linear algebra. So let me just review the concepts from linear algebra, because we're going to be following the same strategy here. So suppose you have a vector v, and then you've got a subspace S, which I'm representing as a plane here, and you want to project the vector v down to the subspace, right? So the projection is denoted by proj sub s of v, right? Projection onto S of the vector v, and geometrically, you do it by dropping a perpendicular from v down perpendicular to the subspace S, and then that point will be the head of the vector, right? So then the projection will be this green vector here. And an important fact about this is that geometrically, the projection here is the closest point in the subspace S to the vector v. Right? And what we mean by close is the Euclidean distance, right? The distance from this point to this point in the usual sense is minimal, right? Well, that's the same thing as L2 error, right? L2 is basically the sum of the squares of the components, and then you take the square root at the end. That's the same idea. That's analogous to taking the integral of the squares of the function and then summing them up that way, and then taking the square root. This is just a discrete version of the same thing. So what we're doing here in projecting is the same thing we want to do with functions. In our case, v is going to be a function. S is going to be the space of polynomials. We're going to want to project the function onto the space of polynomials. And just as you calculated projections in linear algebra by using dot products, we'll be able to calculate projections onto the polynomial space using dot products. We just have to come up with the right notion of dot product. So let me explain the analogy between functions and vectors. They're essentially the same thing. So a vector, you usually think of it as consisting of, well, a point in space. That's one way to think about it. Or an arrow that points from one point in space to another point in space. A 5 vector, usually think of as a sequence of 5 real numbers, right? Representing the components in each of the 5 directions in 5-dimensional space, right? So if boldface v here is a vector, then you can denote the individual components. There's actually various different ways to do it. You can do it with subscripts. In MATLAB, they simply use parentheses to refer to the components of a vector, right? So v of 1 is the first component of the vector, v of 2 is the second component of the vector, and so on. Well, now I want to try to convince you that functions are very similar objects to vectors. So suppose we have a function like f of x equals e to the x. Well, in a sense, this function also has components. That is, you can ask, what's the 0 component of f? Right? You plug in 0 for x, you get 1. You can ask, what's the 1 component of f? E to the 1 is e, and so on. The difference is that the function f has infinitely many components. It has a component for each different x value you can plug in. So in a sense, a function is like an infinite dimensional vector, right? So you can think of functions as being vectors with infinitely many dimensions, right? Vectors in an infinite dimensional vector space. With that understanding, then you can actually perform all the usual operations on functions that you associate with vectors. So for example, you can add 2 vectors. Addition on vectors is defined component-wise. I mean, there's a geometric interpretation also, but you can define it component-wise. You say that f plus w is the vector whose ith component is equal to the ith component of v plus the ith component of w, right? So you do that for all the components. In this case, as I goes from 1 to 5, and that's how you define v plus w. You can define f plus g, where f and g are functions, in the same way. We can simply define f plus g to be the function that when you plug in x, the output is the output from f plus the output from g, right? So that allows you to define the sum of 2 functions. You can define scalar multiplication. Remember, in a vector space, scalar multiplication is when you multiply a vector times a real number, a scalar, and that kind of scales up or scales down the vector. It makes it longer or shorter, but preserves the direction. And again, you do that by simply multiplying this constant c times each component of the vector. So the scalar multiple, cv, is the vector whose ith component is c times the ith component of v. Well, you can do the same thing with functions. You can define the scalar multiple c times f, where f is a function and c is a real number, to be the function whose value when you plug in x is c times the value of f when you plug in x. Right? Now, the next one may be surprising. You can even define dot products with functions. With vector spaces, the dot product was equal to the sum of the product of each of the components, right? So you go through each component, so go through all the indices I for the components, and then you multiply v of I times w of I, right? So you multiply the components against each other and then sum those products. You can do exactly the same thing with functions. You can take the dot product of 2 functions. You simply for each x, you take the product of f of x times g of x, and then you can sum up all those products by taking the integral over x. Right? So you integrate f of x times g of x over the whole domain x, and that is going to behave exactly like a dot product does. Right? And in fact, it will have all the usual properties of the dot product. So you can reconstruct the whole structure of vector spaces, including sums, scalar multiples, and dot products in the space of functions. And that means we'll be able to compute projections of one function onto a subspace of functions using dot products and the notion of projections. So if you have all these features, and if the dot product obeys a few natural properties, then it's called an inner product space, right? So an inner product space is a space in which it's a vector space in which you have vector sums, scalar multiples, and dot products. And the dot product has to obey some specific properties. By the way, the term inner product is more or less a synonym for a dot product. It's just that dot product is what's used in the context of linear algebra, and inner product are what are used more generally in mathematics to represent things like dot products. So the important properties that dot products have to have, there's two of them. One is that it should be symmetric. Oh, by the way, let me point out that on this slide, I'm using Greek letters alpha, beta, and gamma to represent vectors in whatever vector space we're working in. And I'm using A and B to represent real numbers, scalars. So symmetry is the property that alpha times dotted with beta should be the same as beta dotted with alpha. So if the dot product is symmetric, that means that the order in which you apply the dot product doesn't matter. Right? That's a natural thing. It's obviously satisfied for both functions and vector spaces. Right? The order in which you multiply the components doesn't matter. Then there's the property of linearity. So it's basically a kind of distributive property. So it says that if you take a linear combination of alpha and beta, so A times alpha plus B times beta, it's a linear combination of two vectors, and then dot that linear combination times a third vector, gamma, then you can split that up into two terms, one which is A times the dot product of alpha times gamma, and then the other one is B times the dot product of beta times gamma. So in one sense, it says that the dot product with the sum is the sum of the dot products, and it also says that you can always pull out scalar constants. You can always pull them out front. And this is satisfied for both vector spaces and for function spaces, because if you look at the integral, the dot product for functions is defined in terms of the integral, and integrals are linear. They have the property of linearity. So the dot product as defined here will inherit this linearity property from the linearity of integrals, right? Because integrals basically have this property. Now, if you have such an inner product space in which the dot product has these special properties, then you can actually reconstruct a lot of ordinary geometry in the context of this abstract vector space, even if it doesn't seem to have had anything to do with geometry originally. So for example, you can define the notion of orthogonality between two vectors. We can say that alpha is orthogonal to beta if alpha dot beta is 0. Right? So we can make that a definition. If the dot product between two vectors is 0, then we can regard them as perpendicular to one another, orthogonal. We can define the magnitude of a vector to be equal to the dot product of the vector with itself, followed by taking the square root. Right? So the square root of alpha dot alpha. And in vector spaces, this is the sum of the squares of the components, so it's the L2 magnitude. Right? And in function spaces, this is going to be the L2 magnitude also. It's going to be the integral of the square of the function. And you can also define the error, or we could say the distance between two vectors, as simply being the magnitude of beta minus alpha, right? You just take the difference between them, take the magnitude of the difference, and that's the distance between them, or the error. And of course, because magnitude is L2, this is also the least squares error. So therefore, because functions form an inner product space, we'll be able to minimize the L2 error in our polynomial approximation by projecting the function onto the space of polynomials. So let me review what you learned in linear algebra about projections. So again, I'm using alpha and beta to represent two vectors in the vector space. And I think you will have learned all of this on this slide in a course on linear algebra. So first of all, the basic idea is if you have one vector beta and you got another vector alpha, then if you want to project the vector beta onto the vector alpha, what you're doing geometrically is you're finding the closest point on the line that contains alpha to the vector beta, right? So it's like, again, it's like dropping a perpendicular down from beta to the direction of alpha, to the line through alpha, and that's your projection. The formula for it you can give in terms of the dot product. It's going to be alpha dot beta divided by the magnitude of alpha squared. Now this is just a scalar, just a real number, and then multiplied by the vector alpha. Right? And that gives you this vector. Right? It's the vector projection. There's also the notion of the scalar projection, which would just be this, just be the magnitude of the projection. Now, in the case when alpha happens to be a unit vector, then the formula becomes simpler. If alpha is a unit vector, then the magnitude of alpha squared is just 1, so this formula just becomes alpha dot beta times alpha, right? And this is an easier version to think about. I usually prefer to think about dotting onto a unit vector because the formula is easier, and also it's just easier to think about it. You probably learned also in linear algebra that when you take a dot product, you get the magnitude of alpha times the magnitude of beta times the cosine of the angle between them. So in this case, if alpha happens to be a unit vector, that's just 1, and this is just magnitude of beta times cosine theta, and that is exactly, just from basic trigonometry, it's exactly the length of this projection. And then you multiply that length times the unit vector in that direction, and that gives you the vector in that direction. Notice that when you do the projection, you get the projection itself, and then you also get the difference between the original vector beta and the projection, so beta minus the projection onto alpha beta. And geometrically, it's obvious that these are going to be perpendicular to each other, right? So we're able to decompose beta into two mutually orthogonal components, one in the direction of alpha and one perpendicular to alpha. Right? And in fact, it's easy to verify that this difference here, beta minus the projection, is in fact orthogonal to the original vector alpha, and therefore also to the projection itself. You can verify that very easily by computing the dot product. Just verify that when you dot alpha times this, and then use the linearity of the dot product, you'll be able to show that you end up with 0. So I won't go through that, but if you're interested, have a look. But again, the strategy we're going to use here is that by projecting from one vector onto another, we get the closest point onto that vector, and then by combining projections onto a number of vectors in the subspace, we'll be able to get the complete projection onto the subspace. So this is really the most essential tool in projecting onto a subspace, knowing how to project onto a single vector. And then we'll be able to combine these projections to get the projection onto a subspace. And as I said, by projecting onto a subspace, we will be able to get the closest vector in the subspace to the original vector in the sense of L2, in the sense of least squared error. So here's the strategy we'll follow. So in general, if you want to calculate the projection of a vector beta onto some subspace S, and let me just point out that in our case, what we'll be interested in is the case when beta is a function, and the subspace S is the subspace of polynomial functions. And in particular, we'll also be focusing on polynomials just up to a certain degree n, right, up to some finite degree n. Okay, but in general, to calculate the projection of beta onto S, it works the same in any inner product space. What you can do is first work out an orthonormal basis for the subspace S. So an orthonormal basis, as you learned in linear algebra, is just a set of pairwise orthogonal unit vectors. Okay? In our case, those pairwise orthogonal unit vectors will be Legendre polynomials, and we'll discuss them in the next video. Okay? But they will be a special kind of polynomial that will serve as our basis vectors. Once you've got the set of basis vectors, then to project beta onto S, you simply project beta onto each one of the basis vectors and then sum those projections. And the result will be the least squares approximation to beta in the subspace S. I've already talked about how to compute the projection of one vector onto another. The only thing we haven't addressed yet is how to form an orthonormal basis for a subspace. Okay, so as you might expect, there's a way to do that. You probably discussed this in linear algebra. It's called the Gram-Schmidt orthonormalization process. It's rather a mouthful. But it's a method for taking a set of vectors that span a vector space or a vector subspace. So we have some vectors v1, v2 up through vn, and we assume they're independent, so they span some vector space, actually form a basis for some vector subspace. And then what we want to do is we want to convert them from a basis into an orthonormal basis. So we go through this original basis, v1, v2 up to vn, one at a time. For the first vector, v1, all we have to do is normalize it, by which I mean we want to stretch it or shrink it so it has unit length. So all we have to do is take v1 and divide by its magnitude. That'll turn v1 into a unit vector, and that'll be our first element of the orthonormal basis. It'll be a unit vector we'll call E1. Thereafter, for each vector v of the original basis, you have to perform two steps. The first step is to subtract v2, or to take v2 and subtract off the projection of v2 onto the previous basis vector. Right? So we project v2 onto E1. Now, because E1 is a unit vector, I've written the simpler formula v2 dot E1 times E1. That's the simpler formula for the projection. And then you subtract that off from v2. I'm going to call this w2. As we saw, when you take a vector and subtract off its projection onto another vector, the resulting vector is perpendicular to the vector you projected onto. So this vector, w2, is guaranteed to be orthogonal to E1. Right? So by doing this step, we get a new vector which is orthogonal to the first basis vector E1. And then all we have to do is normalize it. So we take our vector v2, divide out its magnitude in order to get a unit vector. And so now we have a second basis vector e2, which is a unit vector, and it's also orthogonal to e1. And then we keep going this way. So let me do one more. We'll define w3 to be the third basis vector of the original basis minus its projection onto the first two basis vectors of the orthonormal basis. So we take the projection of v3 onto e1 and the projection of v3 onto e2 and subtract both of those off from v3. And in this way, we obtain this vector w3, which is guaranteed to be orthogonal to both e1 and e2. And then all we have to do is normalize w3, so it's a unit vector, so we take w3, divide out its magnitude, and we get our third basis vector e3 of the new orthonormal basis. Right? So we keep going like this. So this is the procedure. Again, you probably learned this in linear algebra. And what we'll talk about in the next video is how to apply this Gram-Schmidt orthonormalization process to polynomials to find a basis of the subspace of polynomial functions. And what we'll do, we'll do it for each degree of the polynomial, so we'll have a subspace for each degree n. So we'll have a subspace of quadratic polynomials, a subspace of cubic polynomials, and so on. And we'll see how to get an orthonormal basis for each one of those subspaces, which we can then project onto from an arbitrary function to get a polynomial approximation. Right? So that'll be in the next video.